Hello. Today we are going to before the midterm exam, we finished the GMM chapter, and now we are going to study two-step estimator chapter. So two-step estimator is a very widely used class of estimation methods, and I'm going to show you some examples first. So the leading example in this chapter is the two-stage least square, which is the least square with an instrumental variable. So think about a triangular equations model like this, and say, as usual, x is endogenous variable, and z is the instrumental variable, and we estimate. So the first stage equation is estimated first. So when you have gamma hat, then we estimate x hat, define x hat as this part. So psi, the error term psi may be correlated with epsilon. So we drop this part and only use this part in the place of x. Then we learned how we identify this. And so this is the simplest possible example of two-stage estimation. And it is widely used because you just need to understand the OLS. So you are applying the OLS twice. So applying OLS here first, and then calculate some x hat, and then another OLS here. So its implementation is pretty simple. However, often it's not well understood. So people use this without understanding how it works. So I will explain what you have to be careful in doing this. So that is coming up later. And another example I can show you is the partition regression. So partition regression is, so we divide the regressors into x1 and x2. So suppose that there is no endogeneity. So x1, x2 are exogenous variables, and you are interested only in x1, like beta 1. So you only need x1, but x2 is not necessary, even though it should be included in the regression, but I'm not interested in beta 2. In this case, also remember what is the partition regression model, partition regression idea is, or in some textbook it is called partial out formula. Basically, they are the same thing. And so think about it. The result is, if you regress y only on x1, then what you get is not beta 1 because x2 is not considered. To include x2 in that analysis, you first have to think about this. So regress x1, the variable, the regressor of your interest, on x2, which is the regressors that you are not interested in, and you take the residual because you want to remove x2 from the equation. So we remove this part and just take psi, the residual from this first stage regression, and then regress. And so remember, this is psi. x1 minus gamma x2 is psi. So in the second stage, regress the outcome, the left-hand side variable, on psi. And then the coefficient will be beta 1 because x2 is removed from x1. So psi is uncorrelated with x2. Therefore, regressing y on psi will be consistent for beta 1. So this is another example of two-stage estimation. Of course, you don't need to do it. You can do it in one step. Just regress y on x1 and x2. But just to give you an example what we are doing, I included it as an example. Another example you may have seen is the heteroskedasticity, generalized least square method. In this case, the difference here is I will use matrix notation. y is n by 1, n by 1. So you observe n sample, sample of size n, and then y is a long matrix, long vector, which contains all observations about y. And then x, the thick x is n by k matrix. So k by 1 observations of x is observed for n individuals. So as a whole, you have n by k matrix observations, and beta is usually is as usual the k by 1 factor, and epsilon is now n by 1 factor of error terms. And heteroskedasticity, I guess you have heard about this in like econometrics 1 or undergraduate econometrics. The main problem here is the first observation and the second observation have different variance of epsilon. So observations may have different variances, or they may be correlated with each other. And so we consider a general n by n matrix omega as the variance matrix of epsilon. So it's n by n matrix, which may include correlation between observations or different variance across observations. And then but the problem here is we have to estimate, we need to know the variance to utilize this information. Then what we do here is we first estimate the OLS estimator for beta. So without using any variance matrix, just estimate beta as usual. And then using the estimated beta, we estimate the residual, the error term. Error terms are approximately calculated like this, and then from there you can calculate the variance matrix, replacing expectation with the observed epsilon. And then this matrix can be utilized in our estimation by convert y into y star. Like so, by multiplying omega to the exponent of minus 1 over 2. So this means, so multiplying omega minus 1 over 2 for every one. Then the point here is epsilon star, the transformed epsilon star will have homoskedastic error term. So its error term will be better, is much easier to handle. So now you can apply OLS again. So and the OLS satisfies its optimality, like Gauss-Markov theorem. So it is efficient. It is the best linear unbiased estimator. So this is another example of two-stage estimator, because in the first stage you estimate beta to estimate the variance matrix, and in the second stage you obtain another beta which is the efficient one. So it is very similar to the GMM, optimal weighting matrix estimation. And another example is GMM, optimal weighting matrix example. So in the first stage, you estimate the parameter without using any weighting matrix, or any weighting matrix you want. Like typically, identity matrix is used. And then from the first stage estimation, you estimate the variance of the moments. Variance of the moments are estimated, and using the variance estimator from the first stage, you obtain the efficient estimation in the second stage. So the second stage is more efficient. And another example, Heckmans two-stage estimator. It is really popular. I don't know if you have heard about this, but I think you are going to learn this in applied econometrics taught by Professor Lahiri. So you don't need to know this at this point, but just like listen to this, how it works. So like the main problem. So Heckman, James Heckman is a professor at U Chicago, and he got a Nobel Prize by this contribution. So in 1970s, many economists want to study the wage equation for women. At that time, women's labor participation rate is less than 50%, much less than 50%. So there are two problems entangled in this problem. First, like as I said, many women just don't work for some reason. They choose not to work, right? And second, we are interested in, like, what if a woman is educated, how much she can earn, or what is the return from education for women. So like college premium, is woman's college premium same as man's or not? So the wage equation, or how much woman's kind of wage increases as woman's experience increases, or how much the woman's wage will drop if she has to stop working like for 1 or 2 years due to like pregnancy, for example. So two things: selection, why women don't work, and second, how women's wage is determined in terms of education or experience, or like a career interruption, other blah blah blah. And Heckman, at that time, these two problems are studied separately, and both are kind of biased. But Heckman merged these two problems into one, and suggested a very nice and a very revolutionary method at the time. So the idea is, he first, in the first stage, he estimates the probability of a woman working. So a woman may work or may choose not to work. So he estimates that probability, and he uses that probability in estimating the wage equation. So the wage equation is biased. For example, suppose that I work. So suppose that there are two women. One is working and the other is not working. It is like working and not is not random. It's not randomly chosen. They decide to work or decide not to work. So that implies some information. So if two women observationally the same, but one chooses to work, the other not, then it implies that the woman who does not work is likely to have lower earnings potential, or higher reservation utility. Like for example, she is more satisfied by like raising family, or this woman, like the woman who pursues her career more, is likely to be more ambitious in her career. So these kind of, whether she works or not, has some information in wage. So Heckman suggested to use the probability in the regression, and then he shows that he proved that considering the probability in the regression can adjust the bias, can fix the bias caused by the selection problem. So anyhow, as I described, it goes in two steps. In the first stage, you have to estimate the probability of working, and in the second stage, you have to estimate the wage equation, how the wage is determined using the outcome of the first stage. So use the first stage outcome into the second stage, and you obtain, like for example, the returns to education or the returns to experience, something like that. So that's maybe the most famous example of two-stage estimator, other than two-stage least square, other than two-stage instrumental variable regression model. This must be mostly widely used example. And another example, like maybe the last one. So the last one is, say, Phillips curve. As you know, Phillips curve has a long history, but and often it does not work well. It does not fit, the data don't fit the Phillips curve relationship. So macroeconomists try to fix the curve and try to reconcile the data and the model. And there have been a lot of different approaches. And maybe the most successful one is the expectation augmented Phillips curve. So Phillips curve says when inflation goes up, unemployment goes down, and vice versa. When unemployment goes up, then inflation will go down. They have trade-off. But expectation augmented Phillips curve says inflation is not the absolute. It's not about the absolute inflation, but inflation has to take into account the expectation. For example, if I expect the inflation will be 5% next year, then 3% is minus 2. So 3% is lower than I expected. So it is not considered as a high expectation, a high inflation. And even but if I expected 1%, but the actual expectation was, actual inflation was 3%, then the inflation is higher than my expectation, so it may cause some adverse effects. So anyhow, that is just a basic idea of this theory. And then the problem here is to fit the idea to the data, we need to know the expectation. We have to make up, of course, expectation is not in the data, it is not observed in the data, but one possibility, one way many economists have done is to estimate the expectation of inflation. So assume that people form their expectation of inflation using some information like Z, say oil price and interest rates and many other economic variables, and using those variables, expected inflation takes a linear function. So you estimate the relationship between the past past inflation and the past observations of past economic variables, and we in the first stage we estimate how people would expect the inflation. If they were rational, then economic agents will do this kind of regression by themselves. So expectation will be formed in this way. And then using this expected inflation in the second stage, they estimated an augmented Phillips curve. Anyhow, the content itself is not important at this point, but think about their common structure. And often you need to estimate, so you have a certain final regression model, but you know that the final regression model is incomplete in some sense. For example, some variable does not exist in the data, or you need to know some information to implement the final regression model. Then usually you have to estimate something before you do the final regression model. So this is typical examples of two-stage regressions. And in the next video, I will define a general framework for two-stage regressions, two-stage estimation, and we'll discuss some important points of when you use two-stage estimation. Okay, thank you for watching. See you.